You watch your simulation run perfectly on the screen, tracing its path without a single error. But when you load that program into the physical robot, it swings wide and violently knocks a fixture straight off the table. That crash happens because of a mathematical disconnect. The virtual space on your monitor and the physical reality of your cell are operating on two completely different sets of assumptions. We can permanently eliminate that gap. To do it, we use a rigorous 5-step pre-flight checklist before a single line of code ever reaches the physical hardware. Before we start step 1, check your software version. Updating RoboDK to the latest release ensures you have the current bug fixes and guarantees the features we are about to use function exactly as intended. A simulation is only as reliable as its baseline parameters. Locking down this setup phase guarantees a safe, accurate deployment on the actual factory floor. Step 1 begins in the RoboDK workspace. This is our control room, where we transition from the physical hardware to its digital twin. We start by running the calibration module. This aligns the digital model so its baseline configuration is an exact mirror of the physical unit standing in your shop. To verify the calibration, run a single test movement. You need to confirm that the coordinates in the software match the real-world coordinates perfectly. Next is step 2, configuring your tool parameters. The end effector adds physical drag and inertia to the robotic arm, and accounting for that extra load in the software is non-negotiable. Looking at this wireframe model of the tool, we need to isolate and input 3 critical data points: its functional dimensions, its absolute weight, and its precise center of gravity. Notice what happens when the center of gravity is offset. That shift alters the torque applied to the robot's joints, changing both its physical reach and its movement physics. When you accurately input these metrics into RoboDK, the payload warnings disappear. Your 3D viewer is now perfectly aligned with the real-world end effector. Skipping calibration and tool setup creates a compounding error. A millimeter off at the base becomes a massive positional failure by the time the arm reaches the end of its sequence. Now we move to step 3, aligning the coordinate systems. Think of this as giving both the robot and your workpiece a synchronized spatial map to read from. This diagram shows how we define and adjust the reference frames. We take the mismatched X, Y, and Z axes and slide them into perfect spatial alignment directly over the workpiece. Once the grid is set, we define the tool center point, or TCP. This dot acts as the absolute focal point for every interaction the robot makes with the target. We verify this alignment with a dry run. The TCP must strike the exact target coordinate on the virtual workpiece without any deviation. If a robot repeatedly misses a target while executing what looks like a precise movement, a misaligned coordinate system is almost always the hidden cause. In complex physical factory layouts, operating blindly leads to heavy industrial arms colliding midair, causing massive hardware damage. Step 4 prevents this. We enable continuous collision detection to proactively flag intersection points before the program is deployed. This collision detection system works in tandem with path optimization tools. This allows us to map out safe routes around obstacles without sacrificing tight cycle times. To dial in that efficiency, we adjust specific parameters during the optimization phase: the travel speed, the acceleration curves, and the maximum joint limits. You know this step is complete when you can run the full simulation and see smooth, efficient trajectory lines alongside 0 flagged collisions in the software log. Software-level collision detection is the only barrier standing between a minor virtual miscalculation and expensive equipment damage on the shop floor. As your projects scale in complexity, the program tree can quickly degenerate into an unreadable list of tangled commands. Step 5 solves this by breaking down those massive sequences into small, logical modules. We create distinct separation for individual actions, like pick, move, and place. Structuring the logic into a modular architecture means when an error occurs, you know exactly which segment to check. This approach drastically reduces the time required to isolate and debug the issue later. A perfectly safe and highly accurate program is entirely useless if the internal logic is too complicated for your team to maintain or update. With all 5 steps checked off, you now have a calibrated, collision-free project that exactly mirrors your physical workspace. From here, you can advance to the next level of proficiency by utilizing RoboDK's Python scripting environments to automate your most repetitive programming tasks. Start by applying these workflows to simple, single robot projects. Build your operational confidence on the basics before tackling complex, multi-robot automated cells. As you build, rely on the official RoboDK documentation, tutorials, and support forums for your ongoing training and troubleshooting. Mastering robotics simulation means moving beyond mistake avoidance to systematically engineering predictable, real-world success.